Welcome to the Problems Channel Season 3, Episode 14, the episode which I titled Sisyphus versus Spherical Chickens of Uniform Density, because in this episode we will solve a physics problem in which we will find out how to distinguish between a sphere, a hollow object, and a ball, a solid object, using the methods of classical mechanics. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We suggest that you watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. The best way to ask your question is to find an episode that is of interest to you. Use the comment section in that episode, and I will find the time to answer all your questions. In the physics problem S3E14, we're given two massive objects, a massive sphere, which is a hollow object, and a massive ball, which is a solid object. And without tapping or knocking on any of these objects, we're asked for a way to determine which object is which with absolute certainty and correctly, using presumably the methods of classical mechanics, if we're told that the masses m of both of these objects of revolution are one and the same, and the radii of both objects are one and the same. You are more than welcome to solve this problem in any which way as you see fit, and we definitely would like to hear from you. How did you manage to solve this problem? Share your bright idea with us and with our community in the comment section. Meanwhile, I will present 5 of my solutions of this problem, that all of which are based on the following idea. The moment of inertia with respect to a natural axis of symmetry for both objects, for a sphere and for a ball, which is a straight line that passes through the center of correspondingly a sphere and a ball, is what? For a sphere, that moment of inertia is 2/3 times m mass times r radius squared. And for a solid ball, that moment of inertia is 2/5 times m times r squared. Thus, across two fractions, 2/3 and 2/5, which one is larger and which one is smaller? Exactly. My first solution of the physics problem S3P3 has everything to do with Sisyphus, who was apparently, according to the corresponding Greek myth and legend, a poor guy who was forced to push a rock up a mountain over and over again. And that is precisely the idea that gives the title to this episode: Sisyphus versus spherical chickens of uniform density. That is, for the solution number 1 of 5, I propose that we conduct the following experiment. We take both of the given objects of revolution, a sphere and a ball. We spin them up to one and the same non-zero initial angular velocity omega 0, and then we bring both of these rotating objects to the foundation of an inclined plane, which is basically a plane that is inclined with respect to the horizon by the angle theta, and with no or with zero initial linear velocity. In other words, we do not push any of these objects up the inclined plane. We simply spin them up, bring them to the foundation of this inclined plane, and then we let these objects roll up the corresponding inclined plane, thus mimicking what our friend Sisyphus was supposed to do for eternity over and over again. And the idea here is the following. What is the foundation for this experiment? How will we distinguish with absolute certainty and correctly which of the given objects, visually indistinguishable, is a sphere and which one is a ball? Well, the idea here is the following. As our objects rotate and climb up the inclined plane, they will be executing their motion against gravity. And at some point, gravity will say, no more. And that means that our objects will climb to the highest possible point on the inclined plane. And at that point, they will do what? They will stop. And the idea here is the following. We compute the time that it takes for both objects to climb to their pinnacle on the inclined plane. H stands for time that it takes to climb to the highest point. Sub S for a sphere and sub B for a ball. And then we juxtapose one against the other. And hopefully the idea here is that there will be enough tactical juice in this comparison that will allow us to discriminate a sphere against a ball and thus determine with absolute certainty and correctly which one of these visually indistinguishable objects is a sphere and which one is a ball. And based on my experience, sometimes in physics, students of physics especially get confused between the difference between a sphere and a ball. And for example, to a mathematician, the phrase a hollow sphere or a solid ball sounds like wet water. In other words, a sphere by definition is an object that is hollow, and a ball by definition is an object that is solid. But here and there, just to make sure that especially our up-and-coming physics students are not confused by this difference between the two objects, I will say a hollow sphere or a solid ball, just to make sure that we understand beyond any reasonable doubt which object is which. And now let us undertake this particular computation together. One way to compute the times that it takes our proverbial spherical chickens of uniform density to climb to their pinnacle of the inclined plane career is as follows. At first, when we spin up our object of revolution to an initial angular velocity omega 0, we bring it up to the foundation or to the base of our inclined plane and let it go. At first, this object will be sliding for a certain amount of time, and that means that the force of friction that will emerge between the rotating object and the inclined plane will be the so-called the force of sliding friction, and the slipping phenomenon of the rotating object here means that the linear velocity of the center of mass, O, of either object of revolution will be hovering right around zero. In other words, it will not be, our object will not be propelled forward in a linear fashion, but it will be spinning, roughly speaking, in place, perhaps quite viciously or vigorously, and that means that its linear velocity v will be hovering around zero, but its angular velocity will be greater than zero. But after a while, the object of revolution, our spherical chicken of uniform density, will catch, and it will start rolling up the inclined plane, and at that point the force of sliding friction will transform into the force of rolling friction. That is important to understand. That force of rolling friction will be applied to the point of contact or to the point of tangency between our object of revolution and the inclined plane. Here, that point is shown as T. And the fact that the object is rolling means what? That the point of contact on the object of revolution will have what velocity with respect to the inclined plane? Zero, precisely. Now, that force of friction is shown over here in red. It will point up the inclined plane, and that is the force that will pull our spherical chickens, either that chicken will be hollow or solid, up the inclined plane towards the point, the highest point to which it can climb, this object can possibly climb. And now, once we understand the mechanics of that motion, we can now bring in the formulas, which are what? Well, first, our angular velocity omega t of time, which in this case will be, our object will be rotating this way, will be somehow connected with the linear velocity of its center of mass, E, shown over here in blue, v of t, function of t, in some interesting way. But regardless of how these things are interconnected and how they vary, the law of motion of the center of mass that was inked by Isaac Newton back in 1687 still applies. And if we introduce our reference frame, which runs this way, the proverbial x-axis will run up the plane this way, and perpendicularly to it or orthogonally to it will run our proverbial y-axis. I will not be drawing it in order to avoid the clutter, but we all understand the frame runs x along the inclined plane, y perpendicular to the plane. As such, in its projection onto the axis that runs parallel to the inclined plane, the law of motion of the center of mass will be what? The proverbial ma, which is what? M times the first time derivative of the velocity of the center of mass over time will be our force of friction. And in this case, projecting the force due to gravity mg onto the axis that runs parallel to the inclined plane will give us what? The angle of the inclined plane, or the angle that this plane makes with the horizon, is theta. That means that this angle theta will be formed between what? Between the vector that models the force due to gravity mg and the straight line that passes through the center of our spherical chicken and the point of contact. That will be the smaller here angle theta, which means here for the projection of the vector of the force due to gravity onto the axis that runs parallel to the inclined plane, we will have what? Minus mg times the value of the trigonometric function of sine of theta, even though it is not that important in this case. Now, this is one equation. What is the second equation? Well, the second equation that we will bring in over here, we have what? We have a force of rolling friction applied to the point T, and this gives us the idea the whole thing, our spherical chicken, whether it is hollow or solid, rotates. So this gives us an idea to bring the so-called torque equation of motion. And here we remember what? That the first time derivative of torque, uppercase L, designates torque. In this case, this is a quite pleasant case, will be what? The moment of inertia, which doesn't vary over time, times the first time derivative of the angular velocity of our spherical chicken of uniform density. And that is equal to what? We remember. This is equal to the vector product between the radius vector that connects the center of mass, or the axis that runs through the point of the center of mass of both the hollow sphere and the solid object, runs this way, and the point of the application of force of friction, the application of the force of friction, point T, will be what? In this case, if we translate the vector r that runs from the center of mass to the point of application of the force, for example, this way, then we will count the angle between these two vectors. Remember, the vector product r times f is what? The product of their magnitudes times the sine of the angle between them. But the angle between them is computed which way? In the positive direction or counterclockwise. Over here it will be what? 3 pi over 2. The sine of 3 pi over 2 is what? Is minus 1. So r times the force of friction. These are our two equations, and we are off and running. We can now move on. So from here we see that we have the force of friction. Here we have the force of rolling friction. We want to eliminate it. We do not care about that force right now. What can we do? We can multiply this equation. We can multiply this equation through by r. So we will have r on the left hand side. We will have r over here, r, and we will have r, where I will insert it here, mgr times the sine of angle theta, force of friction F, friction times r, the radius, and then r times m times the first derivative of the linear velocity of the center of mass over time. And now what do? Well, we here cunningly move the minus sign to this side over here, minus sign. This is only for our tactical maneuvering, so I can save some space on the board. And now we insert this result. We take this guy and we insert it over here, and then what will we have? We will have m times r times dv over dt is equal to what? Minus I times d omega dt minus mgr times sine of angle theta. That maneuver should be understood by everyone, nothing complicated. We simply took the expression for the r, the radius of our object, whatever it is, a sphere or a ball. Remember that radius is one and the same. So that radius times the force of friction with the minus sign in front of it, which we carried over. We took it and we inserted into the first equation, which is the equation for what? For the law of motion of the center of mass, which we multiply through by one copy of r. Now we have this result over here. What is the next maneuver? What would you do? Exactly, you will multiply it first. We will multiply it through by dt all the way. The first differential. In this case, what will we have? The dt over here in the denominator will evaporate. dt over here in the denominator will evaporate, and here we will have precisely the first differential over time, dt. Now what? Now we integrate the left-hand side from 0. Remember, 0 is 0. The initial linear velocity was 0 to the current one, v. We integrate this animal from omega 0 to omega. Remember, omega 0 is our initial angular velocity. We spun up our hard-working spherical chickens of uniform density to one and the same angular velocity, and then we'll launch them up the inclined plane. And here we integrate this bad puppy from 0, because this is when the 0 time is when we clicked on the timer. When the object caught and started moving, the race is on. From 0 to t, the current value of time. That maneuver is understood too. So what do we have here is a trivial integral. So we have m times r times v is equal to, here the integral is trivial, we will have I times omega 0 minus omega, the current value, because here the integral of essentially I dw becomes w evaluated between w0 on the bottom, w on the top. I'm sorry, omega minus omega 0, minus in front, signs flip, omega 0 minus omega, minus mg r, again the trivial integral, t times sine of theta. This is our result, very straightforward, nothing complicated. Now what do we do? Remember, we already went through this exercise earlier at the end of the second season, when we solved the problem of finding out what is more difficult to tip over, a cube or a cylinder. We translate spoken English into the actionable mathematics. So how do we translate the spoken English of a spherical chicken of uniform density climbs to the pinnacle of its inclined plane traveling career, climbs to the highest top? Well, when our rolling, at this point, rolling object that rotates and moves linearly up the inclined plane reaches the highest point on the plane, what will happen? Well, two things will happen. Its linear velocity v will become 0. The linear velocity will become 0. And also at the same time, its angular velocity, omega t, will become 0. And conversely, if our object of revolution stops rotating about its axis that runs through the natural axis of symmetry, then it stops propelling forward linearly, which means the linear velocity is 0 as well. So this is our condition. If the center of mass of our object of revolution stopped moving linearly, then it stopped rotating, and conversely, if our object stopped rotating, that means it stopped propelling itself forward linearly, and thus the object reached the pinnacle of its inclined plane traveling career. It climbed to the top, to the highest point that it could possibly climb. So here we have 0. Here we have the moment of inertia times omega 0 minus mg r. The time t becomes t sub h times sine of theta, And from this condition, what do we have? Let's write down our result over here. In general, the solution is the following. The time that it takes our object of revolution to climb to the highest point on the inclined plane, given the initial conditions, will be what? It will be moment of inertia, we'll write it suggestively this way, times omega 0 divided by mg r times sine of theta. This is the result that we will need in the next segment. I will take a short break to erase the board and prepare it for the final computation, but you already see what is going on. This is precisely the condition that we were aiming, that we were shooting for. The time that it takes our spinning and rotating and moving object to climb to its highest point on the inclined plane is expressed in terms of the moment of inertia of that object with respect to its natural axis of symmetry here, the uppercase I moment of inertia. And all the other parameters of this experiment are what? They are exactly the same. The initial angular velocity omega 0 is the same. The mass m by the assumption is the same. The radius r is the same. The acceleration due to gravity g is the same. The angle theta is the same. The sign is on the range of interest is a single valued function. It's one and the same. So this factor over here is one and the same. And it only comes down the difference in times for these two objects of interest, a sphere and a ball, comes down to what? To the difference between their moments of inertia. Exactly. So in the next segment, after I take a short break, we will bring this computation home and write down the expressions for the moment of inertia for a sphere and a ball. As I mentioned at the beginning of this episode, the moment of inertia with respect to its natural axis of symmetry, or a straight line that runs through the center of a sphere or a ball. For a sphere, I sub s, where s stands for a sphere, is given by the expression 2/3 times m, the mass of the sphere, times r squared. And the moment of inertia of a ball with respect to the same natural axis of symmetry is 2/5 times m times r squared. But in our problem, the mass m and the radius r is one and the same in both cases, whether we have a spherical chicken that is hollow or a spherical chicken that is solid. And that means that if we construct the ratio of 2 times that we see over here, all the material in our experiment that remains one and the same regardless of the quality of the object of revolution, the initial angular velocity omega 0, the mass m, the acceleration due to gravity g, 9.8, roughly or approximately 9.8 meters over second squared. The radius r, the value of the trigonometric function of sine of the angle theta is the same. All this material vanishes in the ratio of 2 times that it takes our objects to reach their highest point on the inclined plane is expressed as what is a ratio of the moments of inertia with respect to its natural axis of symmetry. And this expression is shown over here. This ratio comes out to 5/3. This is a number that is strictly greater than 1. Not only that, on the practical side, if we, for example, come up with a decimal expansion of that number, it comes out to approximately 1.666 and so on, let's say 1.67. So on the practical side, it must be quite detectable, and that means that the time that it takes a hollow object to reach its highest point on the inclined plane will be strictly larger than the time that it takes to do the same thing for a solid object, for a ball. In other words, here we can write down the following. The time for a sphere to travel up the plane to its highest point is larger than the time that it takes a ball to do the same thing. So here is our experiment. Spin up two objects visually indistinguishable, same radius, same mass to one and the same angular velocity. Launch both objects up identically inclined planes with the coefficient of friction, all other conditions being equal, and then simply start the timer when they start rolling, and then decide when each object stops, click the timer to stop it, and the clock that shows the largest time between the two corresponds to a sphere, which is a hollow object, and the time that is the smallest corresponds to the ball. And what you just have seen is the minimum viable amount of calculations or work, if you will, that represents hard science, that represents physics, because remember, the computational idea or computational goal of theoretical physics is what is the production of mathematically precise solution of an approximate problem, an exact mathematical exact solution of an approximate problem. Here we have our approximate problem, but at the end of our work that we presented here, we captured our work in the language of mathematics, which means conversely, if at the end of your work you did not produce a mathematically precise and tangible result, whatever you did was not physics, was not hard science. It quite possibly was astrology or psychic reading or whatever it is, but it has nothing to do with hard science. Hand waving, smoke and mirrors does not count, not accepted. This is what you saw is the minimum viable amount of work that needs to be done in order for it to qualify as hard science and physics, a mathematically precise and mathematically tangible result. And the explanation over here, maybe I will come back to it uh, more and more. Again, what is the we why do we observe this particular result? Well, remember that the moment of inertia with respect to, let's say, a natural axis is a mathematically quantifiable quantity that relates to the ability of the object to resist the rotational effort, intuitively speaking again. This is the precise mathematical expression of this idea, but in plain English, if we talk about an intuitive explanation, an ability to resist the rotational effort, or in other words, the moment of inertia represents the answer to the following question: how easy it is to spin up, let's say, this particular object to a particular angular velocity, for example. And if we have a if we have a sphere or a hollow object, remember that all of its mass, whatever it is, all of its mass is located as far away from its geometric center as possible. It means all of that mass must be brought into rotational motion, and the effort to do that must be evidently greater, because we have to, if we rotate this object with respect to its natural axis of symmetry, all that effort must go through the radius, through the entire radius of that sphere. On the other hand, in a ball, exactly the same mass that in a sphere, distance as far away from its geometric center. With the ball, that mass is, let's say, smudged across the ball in some fashion. So it is not the case that all of its mass is as far away from its geometric center as possible. Quite the opposite. We have the some amount of mass immediately next to the center, and then a little bit further, a little bit further, and a little bit further away. And that means that in some sense, again, in plain English and very intuitively, it is easier to bring a solid object like this into a rotational motion, the same style, for example, to spin it up to the same angular velocity, than it takes a hollow object. Easier, harder, harder, easier. And that vague, plain tongue English, easier and harder, translates into hard physically and tangible mathematics over here in this formula, and that represents one solution, or the first solution out of 5 of the problem S3E14. For the second solution of the physics problem S3P3, I propose the following experiment. We take our favorite spherical chickens of uniform density and we put them on top of a stationary sphere. The sphere is shown in white over here of radius uppercase R. We put our spherical chicken of uniform density, whether that chicken is hollow or solid, on top of that sphere. And with the minimal effort, the position of equilibrium here will be obviously very not stable. With the minimal effort, we'll let this object of revolution roll without friction this time along the surface of a stationary sphere. And during this rolling motion, what will happen eventually? Eventually, this object of revolution will separate from the surface of the stationary sphere, or in plain English, that object will jump off that sphere. The idea here is the computational goal of the solution number 2 is to precisely compute the magnitude of the angle of separation theta s, the angle of separation of our object of revolution from the stationary sphere, and then discriminate a hollow object against its solid counterpart based on the angle of separation theta s, s for sphere, b for a ball. And then again, the idea here is that there will be enough tactical juice in this juxtaposition of these two angles of separation that will allow us to determine with absolute certainty and correctly which of the two given visually indistinguishable objects of equal mass and equal radius is a hollow object, a sphere, and which object is solid or which object is a ball. Now, once you understand what is going on over here in this experiment, I propose that you put this video on pause, walk away, try to solve this problem on your own, and then come back and compare your solution to ours. This particular problem can be solved in a number of different ways, using, for example, the Lagrange multipliers, but the objective of this episode is not to explore the mechanics of the Lagrange multipliers, but to explore how a problem can be solved and how a particular experiment in order to solve a given problem can be put together, because we are in charge, we're in control. We come up with a number of what we think reasonable assumptions, and then we take these assumptions all the way home. So as simple as possible, but not simpler. What is going on during the motion of the rigid object of revolution as it moves along the outer surface of the sphere R? Well, there is always the reactionary force, that is the normal force, that is, let's say, applied to the center of mass of the given object. And because the surface here is a sphere, the vector of the normal force n is a vector that is passing through the point of contact, or let's say through the center of mass and the center of a given sphere in a radial direction, like so. But the idea here for the computation of the angle of separation is the following. When and if the given rigid object of revolution separates from the sphere, then what happens? Then the reactionary force and vanishes, becomes zero. That's exactly the condition. So if we take our axis along which the interesting forces apply, that points this way from the center of our object of revolution, that points towards the center of our stationary sphere of radius uppercase R, then in projection onto that sphere, what will we have? We will have our MA, that is, well, let's say at the time of separation, MAS will be the square of the separation velocity divided by the uppercase r plus lowercase r, because this distance over here is evidently what? Uppercase r plus lowercase r towards the center of mass of the spherical chicken of uniform density, be that chicken hollow, modeling a sphere, or solid, modeling a ball, is this distance right here. And that is what? mg times what trigonometric function? Here, remember, we have two parallel straight lines. For example, this straight line that runs through the center of our stationary sphere. In this parallel straight line that runs along the vector that models our force due to gravity, mg, and we have a straight line falling on these two straight parallel lines, then according to what? Euclid's Elements, Book 1, proposition this and that, if a straight line falls on two parallel straight lines, then the angles here and here are of equal magnitude. So we have the cosine of the angle of separation, theta s, on one hand. So what do we have? M and M cancel each other out. So right away, for the cosine of the angle of separation, theta s, what do we have? We have v squared s over g times uppercase r plus lowercase r. You see, but here is an important thing. Our object is rolling or moving over the outer surface of the rigid stationary sphere in such a way that there is no slipping and there is no sliding, gliding, any of that stuff. So that means that the angular velocity of this object and its linear velocity v are locked into this relationship right here. The linear velocity v is equal to omega times r at all times, including the time when the object separates from the sphere. And that means that for the cosine of this angle of separation, we have omega squared s times r squared divided by g, the acceleration due to gravity, plus r. That's very well. Now, how do we compute the angular velocity omega s of separation of our object, of rigid object of revolution, when it jumps off the rigid stationary sphere? Well, we can use for example, the law of conservation of total mechanical energy, again, because there is no friction. Again, we're in charge, we're in control. We impose the conditions onto a given experiment. The two surfaces are very smooth. We ignore the friction, of course, is always there, but it's so negligible we choose to ignore it. So in this model, of course, our separation angle will also be an approximation, but we think that our model is quite reasonable. So here, using the law of conservation of total mechanical energy, we see that precisely because there is no friction in our system, the potential energy that was expanded while the center of mass of our uniformly dense spherical chicken was displaced vertically by this distance right here, that potential energy was expanded on what? mghs was expanded on to the kinetic energy associated with the linear option, mv squared s, the velocity of separation over 2, plus the energy associated with rotational motion, I, the moment of inertia, times omega squared s over 2. So now we can take the expression for, remember, the velocity v s, the linear velocity v, is equal to omega s times r. We put this expression over here, and what do we obtain? We have m omega squared s r squared over 2 plus the moment of inertia times omega squared s over 2. And if we factor out this common term, what will we have left? Let's do that. Omega squared s over 2. What will be in the parentheses? mr squared plus the moment of inertia I. and this is equal to mghs. So for the sought after square of the angular velocity of separation omega s, which sits over here in the numerator, what do we have? Let's write down this expression. Omega squared s is equal to, from here, 2mghs divided by mr squared plus I. You see from here, 2 goes into the 2 in the denominator goes into the numerator on the left hand side. 2 in the denominator of the right hand side goes to the numerator on the left hand side, 2mghs, and this factor goes into the denominator on the left hand side. Voila, we have our expression. Now what do we have? We have the unknown quantity, the separation height hs, but that separation height can be recovered from the pure geometry of the problem. No physics, raw, pure mathematics, if you will. What is this separation height? Well, that's this distance right here, lowercase r plus uppercase r minus the projection of the same over the angle theta s. So it will be lowercase r plus uppercase r, this is also uppercase r, times the cosine of the angle theta s. Let's write it down over here. hs is equal to uppercase r plus lowercase r times 1 minus cosine of theta separation theta s. That is straightforward, this little distance right here. From this distance, we subtract the projection of the same, and this is this line segment right here. So let's substitute this expression, let's substitute it over here. So we will have 2mg divided by mr squared plus I times r plus r times 1 plus 1 minus cosine of theta s. This is the expression for omega square s. Now we inject it over here for the cosine of theta s. So what will we have? We will have cosine of theta s equal to, let's write down r squared over this expression, g r plus r times the square of the angular velocity of separation, omega squared, which is this expression right here. So 2mg r plus uppercase r plus lowercase r times 1 minus cosine of theta s divided by mr squared plus the moment of inertia I. What do we see? We see that the acceleration due to gravity g cancels out. The sum uppercase r plus lowercase r, uppercase r plus lowercase r cancel out. And what do we have? We have a nice expression. Now make sure I give you time to put this video on pause, take good notes of this, because now I will erase this. This is all straightforward material. You should have no problems figuring this out. So the cosine of theta s comes out to be equal to what? 2 g and g cancel out, 2mr and equal to 2mr squared divided by mr squared plus the moment of inertia I times 1 minus cosine of theta S. That much should be evident. Here I forgot the square, mr square, from our previous expression that was omega square s r squared. So this is the equation for the cosine of theta s, the angle of separation. Let us solve it together. It's not complicated at all. What will we have? We'll have two factors. One of the factors associated with 1 and 1 with here. So we will carry this factor to the left-hand side, and we will factor out cosine of theta s right away. We will have what? 1 plus this 2mr squared divided by mr squared plus I equal to 2mr squared over m lowercase r squared plus the moment of inertia. You can see we can see the light at the end of the tunnel. We see what's going on here with this guy. So once we bring these two terms to one and the same denominator, mr squared plus 2 copies of it will be 3mr squared. So cosine of theta s is equal to times, let's do it slowly, 3mr squared plus I divided by mr squared plus I is equal to 2mr squared over mr squared plus I. Again, the denominators in both cases cancel each other out, and what do we have for the expression of the cosine of the angle of separation theta s? We bring the numerator on the left hand side into the denominator on the right hand side, and voila. Let me erase this. We'll understand where did these manipulations come from, and let us write down the expression that we were looking for. Cosine of theta s is equal to 2mr squared divided by 3mr squared plus the moment of inertia, uppercase I. This is the result that you were expected to obtain on your own. Make sure this is the result that you have. Now I will erase these manipulations over here, take a short break, and we will bring this computation home again by injecting the specific expressions for the moments of inertia. This time the moments of inertia quite straightforward with respect to the natural axis of symmetry of a sphere and of a ball. The final computation is less than trivial. Into our expression that we developed in the previous segment, we inject 2/3 mr squared for the moment of inertia of a sphere with respect to its natural axis of symmetry, and we put 2/5 of mr squared for the moment of inertia of a solid ball with respect to its natural axis of symmetry. Now we see that mr squared will cancel out everywhere. So for the cosine of the separation angle theta s for a sphere s, we get what? 2/3 plus 2/3. Multiply everything by 3. 6 in the numerator, 9 and 2 is 11 in the denominator. If you look at the decimal expansion, look it up in tables or compute it by hand somehow, you will see that this magnitude will be 56 degrees, 0.944, let's say, up to the first 3 decimal significant digits. And for the expression for the cosine of the separation angle of the ball, we will have the same expression, but 2 in the numerator, 3 plus 2/5, multiplying both sides by 5, we get 10. 15 plus 2 is 17, 10 17th. Again, if you somehow care to look up the decimal expansion for the absolute value of the magnitude, just to get an idea of what is going on here. You will see that this magnitude will be 53 degrees, 0.968, up to the same 3 points, and it's basically here the delta, let's say the delta is roughly 3 degrees difference, approximately, again, of course, plus minus, but it's quite detectable. It's quite detectable. 3 degrees is a healthy margin, so to speak, for precision. It is quite possible to detect these things. It's quite detectable. But fundamentally, what we see is the following. On the subset of real numbers of interest, meaning between the angle of what? What can it possibly be? Well, 0 to, of course, pi is an overkill. We actually, by the looks of it, need only the subset from 0 to pi over 2. On that subset of real numbers, the trigonometric function of cosine is what? If this is 1, if this is, let's say, pi over 2, the trigonometric function of cosine is what? It's continuous and it's monotonically decreasing. It's monotonically decreasing somehow this way. That means that to the larger value of the cosine, they corresponds what? A smaller angle. Exactly. Exaggerating for demonstration purposes, larger value here corresponds to this angle, and a smaller value of the cosine corresponds to exactly what? Larger angle. So this is angle for the sphere, and this is angle for the ball. Sphere and ball, and the sphere evidently is larger than angle of the ball. And how can we do that? Well, let's juxtapose 6/11 against 10/17. 10/17. So what is the relationship between them? 6 times 17 is 102 over 11 times 17, and here we will have 110 versus 11 times 17. So evidently 110 is larger than 102, purely theoretically, without any calculators or any other aid. We know purely theoretically that to the larger value of the cosine, there corresponds a smaller angle precisely because on the subset of real numbers of interest, 0 to pi over 2, our friend over here is continuous and is monotonically decreasing. Game over. So the result over here is that the angle of separation for a sphere will be strictly larger than the angle of separation for the ball. Consequently, we conduct 2 experiments, 2 stationary spheres, rigid, stationary, the same radius. We roll 2 objects visually indistinguishable from the top of the sphere with a very gentle nudge. Everything we try to keep identical, and then we simply detect the object that's separated from the sphere at an angle that is larger between the two corresponds to a sphere, and the object that's separated from the stationary sphere earlier in terms of degrees with the smaller angle corresponds to a ball. So this is sphere larger, ball smaller. This time the angles came out to be quite detectable. Again, what you just saw, what just transpired over here, is the minimal viable amount of work that has a chance to pass for hard science and for physics. Anything less than this is not hard science, is not physics. It's hand waving, smoke and mirrors. Perhaps it's astrology, perhaps it's psychic reading, but it has nothing to do with physics and hard sciences. Remember, the computational goal of theoretical physics is the production of a mathematically exact solution of an approximate problem. Mathematically exact, mathematically precise solution. On the far end of our experiment, there sits hard, tangible mathematics. Then we have a chance for this work to pass as a hard science. Anything less than that has no chance. We may have made a mistake in physics, for example. This is bad. We should not really be doing that. and our mathematics will be completely off. Or we may have made no mistake in physics, but we made some silly mistake in mathematics. Happens to the best of us all the time, all day long. Doesn't really, it's not the best thing, of course. You should do both physics correctly and mathematics correctly. Here we've done both correctly. That's the result. And again, if there are any people in our audience who are more inclined towards the experimental side of physics, I'm not that good with experimental physics. I mostly deal with the theoretical part. You may tell us how you can share your ideas in the comments with us. How can you detect physically, if we were to conduct this experiment, how can we detect this angle? What is the idea for detecting this angle? Shine some light. When the light starts coming through, boom, we know. Or I don't know, run the electricity. When the electricity, uh, when the ball is on the sphere, the chain is, our circuit is closed. There is electricity. Once it jumps off, the circuit opens up. Some whatever contraption you can come up with, share your experimental ideas with us. Now that was the solution number 2, and next we will move on to the solution number 3. My third idea for solving the physics problem S3B3 is the following. We take a stationary, smooth, rigid cylinder of radius r, shown over here. This is the surface, partially, that surface is shown over here. This is a cylindrical surface over here. It is stationary, let's say. And inside, on the inner surface of that stationary cylinder of radius uppercase r, we drop our rigid objects of revolution, our proverbial spherical chicken of uniform density that is hollow, modeling a sphere, or our proverbial spherical chicken of uniform density that is solid, modeling a ball. And we observe these objects execute the so-called small angle oscillations about or with respect to the position of stable equilibrium over here at the bottom of the cylindrical surface. So our objects, our spherical chickens, roll back and forth. This time also no friction, no slipping, the pure and raw definition of rolling. And as they roll, they execute their center of mass, let's say, executes actually a small angle oscillation. Tick tock, tick tock, tick tock. The idea here again is to compute the period of small angle oscillations of the center of mass of either a sphere or a ball. And the idea, again, when we begin solving a problem, we do not know if this idea will pan out or not, but the hope here is that there will be enough tactical juice again in this comparison, so that when we juxtapose the period of small angle oscillations of a sphere versus the period of the small angle oscillations of a ball, we will be able to discriminate one against the other and determine with absolute certainty and correctly which one of these two visually indistinguishable objects is a sphere and which one is a ball. And again, we can see that the moment of inertia, we again hope already we see what's going on. The moment of inertia will somehow have to work in to that period of oscillation in a prominent way and help us distinguish these two objects. So now that you understand what the problem is, what's the basic idea, you can put this video on pause, walk away, and try to solve this problem on your own, then come back and compare your result with ours. And in the next segment, we will carry these computations out together. Because I want to keep the size of this episode manageable so most of the students can watch this episode in its entirety, I already pre-wrote the gist of the solution of this problem on board for you. I will go over it together with you. And that solution is based on the idea of modeling the motion of our solid in this case with the so-called rotation about an instantaneous axis with the angular velocity omega. In this case, the instantaneous axis will pass precisely through the center of mass of our uniformly dense, either a sphere, massive sphere, or a massive ball. The distance of that axis, instantaneous axis, is located how many units of distance away from the center of our cylindrical surface. Well, evidently uppercase R minus lowercase r shown in blue over here, and that type of motion about an instantaneous axis of rotation with an angular velocity omega is closely connected to the so-called Euler's rotation theorem. You can look it up on Wikipedia or in your favorite textbook. So here we will step as follows. First, the linear velocity of our center of mass shown over here, the linear velocity v, is written in a straightforward manner. On the one hand, it's the difference uppercase r minus lowercase r. It's this distance right here, starting from here all the way to the center of our cylindrical surface, this distance, times the first time derivative of the angle theta. So the dot notation over here is a typical notation used in physics, in theoretical physics, that designates the first time derivative, two dots, the second time derivative, and so on. It's not very scalable, but that's what we do in physics. So that's on the one hand. On the other hand, because there is no friction and there is no slipping, we have rolling, the pure rolling, we can write down the linear velocity of our center of mass of our rigid body object of revolution as the product of its angular velocity omega times the radius r. So this radius r is shown over here in blue. The rigid spherical chicken of uniform density is shown in blue. Also over here, this radius r. And from that expression over here, from this expression, we write down the expression for the omega, for the angular velocity of our uniformly dense chicken. Remember that it rolls, and as it rolls inside over the inner surface of a rigid cylindrical surface, it rotates, and rotates how? Well, with the angular velocity omega. So from this expression, it is trivial to write down that the angular velocity omega of our rotating spherical chicken is what? Is the ratio of uppercase r minus lowercase r to the lowercase r times the first time derivative of the angle theta, because over time this angle, small angle, varies somehow in a periodic fashion. Now, next we bring in the so-called Koenig's theorem, according to which the kinetic energy K of our object of revolution comprised of what? Of two parts: the rotational, the kinetic energy associated with the rotational part of the motion, and the linear motion. So the rotational part of the kinetic energy is a traditional moment of inertia times omega, the angular velocity squared, over 2 plus mv squared over 2. V is the linear velocity, but we steal the linear velocity from this expression over here. So this comes into here. So it's the same thing. Uppercase r minus lowercase r squared times the first time derivative of theta squared, of course, over 2. And once, let's say, I will mark it over here. If we grab this expression for omega and place it over here, and then we factor out the common bits, this is what we get. This will be the common bit. The difference uppercase r minus lowercase r squared over 2 times the square of the first time derivative of theta, and this will be the material in front of it. Now we go back to the potential energy, U, which is what? Mgh theta will be h depends on theta, of course, is this little bit. So if we draw a concentric circle of radius, what again? Uppercase R minus lowercase r. It's exactly pretty much the same deal as we saw in the previous segment where we had this chicken rolling off the surface of the rigid sphere. But this time, instead of r plus uppercase R plus lowercase r, this is the difference from the distance that is what? Uppercase R minus r here. We subtract the projection of the same onto the vertical, which is what? Given by the cosine of the angle theta. So I wrote it for you over here. The height h theta is uppercase R minus lowercase r times 1 minus cosine of the angle theta. That much should be understood by everyone. This is pure middle school geometry, nothing beyond it. Now we bring a little bit more than middle school. We take the Taylor expansion of the trigonometric function of cosine. Remember, it carries which powers? Even powers of the argument. So in the first, let's say, approximation, or in the second approximation, it will be 1 minus theta squared over 2. 1 and 1 cancel out. The positive copy of theta squared over 2 remains. So this will be our height. We go back here and we say the potential energy U is mgh theta, this expression shown over here. We bring in our happy Taylor series expansion cancellations into this expression. Why did we do it? Well, we did it because the angle theta, let's say over here, small angle oscillations mean that by absolute value measured in radians, this angle is small, much smaller than 1, and this expansion is depicted over here with an approximate sign. So we have an approximation. This is our model. But anything that follows is, remember again, mathematically precise, mathematically exact solution. So this is our expression. Kinetic energy, potential energy. Now, separately, the kinetic energy will vary in some periodic fashion. And separately, the potential energy of our rolling and oscillating spherical chicken will also vary in some periodic fashion. But the trick is that as a fundamental law, their sum, k plus u, will remain constant over time. That is why we can differentiate it over time. This is a standard maneuver and good things can happen. So here we write down the expression for the kinetic energy plus potential energy, constant over time. Basically steal this expression over here, this expression over here, no magic, glom them together. And here, the things in front of theta remain constant at all times. The mass m, the acceleration due to gravity, the difference, all these numbers are fixed. 2 is constant, the moment of inertia is constant, everything else is constant. So we simply, for the purpose of computational convenience, designate this material as alpha and this material as beta, is shown over here, beta alpha. So now we have this expression that basically is what? Is a mathematical manifestation of the law of conservation of total mechanical energy over time. K plus U is constant, K plus U is a constant. This is all we care about, the angle theta. Now we differentiate this relation shown over here, basically, if you will, in plain English, the law of conservation of energy, total mechanical energy, by time, once. And what do we have? 2 is not 0, can be safely canceled out. So we will have alpha times 2 times theta dot times theta dot dot second derivative plus 2 times beta times theta dot the first derivative. 2 is canceled out. It's not 0. It's safe to divide by 2, eliminate it. And we factor out the first derivative, first time derivative of theta. We carry it out. Now we have a product of two terms. The first time derivative of theta plus this beautiful expression over here equal to 0. What does it mean? It means that either one is equal to 0 or the other or both. Now let's analyze the first case when theta dot the first time derivative of the angle theta is 0. What does that mean? That means that in this case the magnitude of the angle theta remains what? Remains constant, one and the same. This is not good. This is not realistic. In our case, the angle theta varies over time. So here we did mathematics right, but physics, which in this case prevail, does not agree with mathematics. So this means that we eliminate this case. This case is thrown out. We do not consider this as a physically reasonable thing that can happen in our experiment. Cannot happen. So that means only one choice. We have alpha times the second time derivative of theta plus beta times the theta itself is equal to 0. Divide both sides of this equation by alpha, which is never 0, and obtain the expression shown over here. The second time derivative of theta plus q squared times theta is equal to 0. Q squared is designated basically beta over alpha, and I designate it as a square. It will be evident why in a few seconds. And again, for everyone's convenience, here is the expression that I pre-computed for you. Q squared, which is beta over alpha. Beta over alpha. Once you cancel out the material that can be canceled out, you will see that you will have this expression. In the parentheses, 1 plus the moment of inertia I over mr squared times the ratio of the difference uppercase r minus lowercase r, and g in the denominator, the acceleration due to gravity. This is again quite straightforward. Perhaps the most difficult part in all of this was to come up with these observations, how to tie together the linear velocity of the center of mass with its angular velocity, and bring in the Koenig's theorem, and overall tie the whole thing together with the motion of the objects with respect to an instantaneous axis here shown that passes through the center of mass, that moves somehow in a periodic fashion back and forth about the equilibrium position shown at the bottom of the rigid cylindrical surface over which our chickens roll. And this is it. If you have never seen this equation in your life ever, this will be scary, and I will tell you how to deal with it in a second. But if you already know what is going on, you can skip the next segment and move on without my help. But bottom line, cutting to the chase over here, this ordinary differential equation is well studied, well known. We know how to solve it analytically. I'll show the steps in the next few seconds. They are not complicated. We already dealt with a similar equation in our previous episodes when we solved the so-called Lanchester's square law and the problem of a bead sliding off of the rotating needle, let's say. The equation there was with a minus sign, here with a plus. It doesn't really matter. We still can do it. But the idea here is that in some sense, we do not really need to solve this equation because we already know what the solution is. It is the trigonometric function of sine or cosine, depending on your taste. The idea is that either the trigonometric function of sine or the trigonometric function of cosine is 2 pi periodic. So we already know that the period of oscillation, small angle oscillations thought after t, will be what? It will be precisely t will be 2 pi divided by q. This is the whole reason for these manipulations, is to this, because qt is equal to 2 pi. When we add 2 pi to the argument of the trigonometric function of sine or cosine, it becomes exactly the same. It returns exactly the same value. That is why these functions are 2 pi periodic. So the game is over. We know q. We can now compute our periods of oscillation in terms of specific moments of inertia I, and we will do it in a few seconds. Again, those who know how to solve this equation can skip the next segment. Those who do not know how to solve these equations can watch the next segment. Again, this segment is optional only for curious travelers who want to see how this equation can be solved analytically, and that process is known as separation of variables because this ordinary differential equation of order 2 happens to be linear is an equation with separable variables. So the way we step over here is as follows. We grab this guy and then we, let's say, carry this term to the left-hand side of this equation like so. We will write it as the second derivative is equal to minus q squared times theta. And then what will we do? We will spell out the definition of the second derivative, which is what? Let me erase it over here. I will dance around this thing, but you guys understand what's going on. It's the first derivative of the first derivative, d over dt. You see, this is a standard maneuver. So far, so good. Multiply both sides of this equation by dt. Here, dt evaporates, and here it shows up. dt equal. What is the next maneuver? The next maneuver is to multiply the result through by the first derivative again of the angle theta. On the left hand side, we keep it as it is. Look at this. Theta dot d theta dot is equal to minus q squared theta dt times. Now here on the right hand side, we spell out the definition of the first derivative, which is what? Exactly. D theta over dt. What do we see? The first differentials cancel out, and what do we have? Minus q squared theta d theta. Game over. Now we have the following result. Theta dot d theta dot is equal to minus q squared theta d theta. Here we integrate both sides of this equation for the first time. Integrate and let's say integrate, but here again, depending on the different problems, have different initial conditions. Here, let's say we rolled up our spherical chicken to some small angle and then we just let it go. So the initial velocity of the chicken was 0. So from 0 to the current one, theta, that we integrate. Here, this guy we integrate because we rolled them up a little bit over the interior surface of the cylindrical contraption that we have. From the angle theta 0, there was some angle, to the current one. So what do we have? Well, these are the trivial integrals. Something squared over 2. 2's will cancel out on both sides. So what will we have over here? Evaluated at the upper boundary, we will have theta dot squared. And what will that be equal to? Well, that will be theta squared minus theta 0 squared, but there is minus in front of it, so we write it as follows. Q squared times theta squared 0 minus theta squared. This is trivial middle school. I exaggerate a little bit, but this is a trivial manipulation. Now what do we have? We have it that theta dot, technically, to be mathematically rigorous, we have to write plus minus q square root of theta squared 0 minus theta squared. You see why? Because when we extract the square root from both sides, here we will have plus or minus theta dot, here we will have plus or minus q in the first power. So we collect all this on one side, over here on the right hand side, and there you go. We prepare our equation for the integration for the second time. We separate the variables for the second time. What is this theta dot? Tell me, what is this? Well, theta dot is d theta over dt. So what do we do here? We multiply this result through by dt. So d theta equals dt. The theta related material is only this guy. Swing them to the left hand side. So we have d theta over square root of theta squared 0 minus theta is equal to plus minus q dt. You see variables separated. That's the final separation. Integrate from 0 to t, current value, from what do we have here for d theta? We integrate again from theta 0 to current value theta. This integral comes out to be trivial, plus minus qt. Now, this integral over here is actually the also a trivial integral. This is what you study in high school. Here we have some freedom of choice for the substitution. For example, this angle theta, let's write it down over here, can be substituted which way? Theta equals theta 0 times, let's say, sine of x. You see, then d theta becomes theta 0 cosine of x dx, but the square root of theta 0 squared minus theta, in this case, becomes what? 1 minus sine squared is again cosine squared, and square root is taken, so we have theta 0 cosine of x. Once we divide all this beautiful mass through, like so, things cancel out, only dx remains, so our integral is equal to integral of dx. This is x, and what is x? Reverse substitution, it will be arc sine of theta divided by theta 0, and this is how these integrals can be evaluated. Again, this material here is not really needed for this particular problem. We can take it as given and known, but this is the gist of how you integrate. And then in general, once we have our solution, we will have, let's carry this thing through. Arc sine of this expression is equal to plus minus qt. What do? You go back, you take the sine of both cases, and then you have that, what was the expression? Theta of t is equal to theta 0 times sine plus minus qt. Usually people put some delta over here, which again can be determined more specifically from the initial conditions, but in our case, let's say this is what we have, sine of qt. And what is the sine? What is the role of this plus minus thingy? Well, sine is a function that is, let's say, odd. So if we, let's say, put the negative, we keep the negative sign over here, we can carry it through. So that simply means from which side of our axis, let's say positive or negative, we let our object of revolution roll inside the cylinder. It doesn't really matter. It is not substantial. We can take, for example, the plus sign. So now you see that once the value of qt reaches 2 pi, when qt is equal to 2 pi, then t becomes uppercase T period, and from here we have 2 pi over q as our period of small angle oscillations. This is it. This is very straightforward. Again, make sure that you remember this. Was arbitrary choice. We could have picked the trigonometric function of cosine over here. Then there will be arc cosine. Here there will be cosine. So depending on how you want to play it out, you can pick either function, and be careful with the so-called initial conditions. Here again, remember, the initial conditions are not that important for us. What is important is the technical physical essence of the small angle oscillations executed by the center of mass of our spherical chicken of uniform density. That is what's important. So once we obtain this result right here, that's it, game over. We slug in our expressions for the moment of inertia and we solve the problem. And now that we understand where did the expression for the period of small angle oscillations of our spherical chickens of uniform density t equal to 2 pi over q came from, we can bring our computation home. And I just went over my records. The expression that you see over here is correct, but in the previous segment where I computed q squared, I think I mistakenly, there was a typo. I showed you not the q squared, but actually q minus squared, q raised to the power -2, not 2. We got to flip this ratio upside down. This one is correct over here. So instead of moment of inertia I, we put 2/3 for the moment of inertia of a sphere with respect to its natural axis of symmetry. What do we have? 1 plus 2/3. 3 plus 2 is 5 over 3. This is the expression for the period of small angle oscillations of a sphere. It's important over here that we have 5 over 3 plus the rest, whatever it is. And if into this expression we inject the expression for the moment of inertia of a ball with respect to its natural axis of history, axis of symmetry, I'm sorry, 2/5 mr squared cancels out. 1 plus 2/5, 5 plus 2, 7, 7 over 5. So this is 7 over 5. Game over if we construct the ratio. If we construct the ratio of these two periods, the period of the small angle oscillations of a sphere and the period of small angle oscillations of a ball, then it comes out to square root of what? 25 over 21. 5 times 5, 3 times 7. So this is definitely larger than 1. From here we conclude that the period of the small angle oscillations of a sphere will be strictly larger than the period of small angle oscillations of a ball. How big this number is, I think you guys can keep me honest and verify, check it with your calculators. That number is not that much different. Well, it's what was the number? 1 point, I think it was something like 1.09 something. So maybe it's not as pronounced, but still purely theoretically it takes longer the a sphere to execute an identical small angle oscillations than it takes a ball. So if we have the members in the audience who are better with the practical side of physics, they can tell us how this experiment may be devised. And I think this is an interesting problem in its own right that can stand on its own. One more time before we break for the next problem, I want to make sure we all understand that the expression that you guys saw in the middle of the screen a couple segments ago, that's my typo. That was supposed to be over there. You were supposed to see q minus squared, and whatever followed then it was correct, because here we flip it upside down and this is what we have, because normally this expression sits in the numerator for the symbol q. This is it for the solution number 3, and next we will move on to the solution of the problem S3P3 number 4. My fourth idea for solving the problem at hand was to turn our spherical chickens of uniform density, a sphere or a ball, into what is known as a physical pendulum, and basically let our spherical chickens perform, again, small angle oscillations, by this time not by rolling inside the rigid cylindrical surface, but simply oscillate about a pivot point Z, shown in red over here, that is located on the periphery of this object, on the periphery, on the outer surface of the sphere or outer surface of a ball. And again, hope that once we compute these periods of small angle oscillations of these objects as physical pendulums, then it will be enough tactical juice in these formulas, so which will allow us to discriminate a hollow object from a solid one. The solution of the problem in this case will be very short and sweet, because here I will take a strictly utilitarian approach. We will just use the prepackaged results. We will not be deducing any of these results, and grab the ready-made formula shown over here. The period of small angle oscillations of a physical pendulum is equal to 2 pi times the square root of the moment of inertia of that pendulum with respect to the axis that passes through the pivot point. And in this case, the pivot point passes precisely through the point Z, perpendicular to the screens of our monitors, perpendicular to the board, like so. Maybe I can even show it better with the pencil, like so. This is our axis with respect to which we will be computing the moment of inertia, divided by the mass of the physical pendulum times the acceleration of the free fall times d, where d is the distance from the center of mass to the pivot point Z. In our case, evidently d is equal to r, because that is the distance from the center of mass to the pivot point Z that sits precisely on the periphery. That is, again, we are the designers of the experiment. We're in charge. We're in control. This is what we do. We put the pivot point over here, but again, you can experiment with putting his pivot point on for this physical pendulum somewhere else. And pretty much the game is over almost right then and there, except for we need to remember which theorem. We need to remember the Steiner-Huygens theorem, or the parallel axis theorem, which says that the moment of inertia of our body, of our object of revolution about the axis that passes through the pivot point, is equal to the moment of inertia of that object that passes through its natural axis of symmetry, plus the mass of the object at hand times the distance squared for between the center of mass and the pivot point. Again, because d is equal to r, we simply put r over here and the game is over. For the moment of inertia of a sphere about the axis that passes through the pivot point Z, we get 2/3 plus 1, which is what, again, 5/3 mr squared. And for the moment of inertia of a ball with respect to the axis that passes through the pivot point Z, again, we take the moment of inertia with respect to its natural axis of symmetry that passes through the center, physical center, geometric center, which is 2/5 plus, again, md squared, but d is r, so mr squared, 2/5 plus 1, 5 plus 2 is 7, 7 over 5. And once we put these numbers, this number and this number, back into this formula, m will cancel out in both cases, m and m. And remember, we have 2 copies of r, and here d 1 copy of r, so we have r over g, r over g. I rewrote these expressions more suggestively because, again, once we construct the ratio, we'll see that the material that does not vary, that remains the same. vanishes. 2 pi square root of r over g, 2 pi square root of r over g. So what will we have for the ratio of square root again of 25 over 3 times 7 is 21. So amazingly enough, the actual expressions for the periods of small angle oscillations of our spherical chickens of uniform density in this case came out to be different. Compared to the answer we obtained in the previous. Remember, in the previous segment, in the problem number 3. But their ratio, look at this. This is interesting. Their ratio came out to be actually 1 and the same. Again, the number is strictly less than 1. It is probably not as pronounced as we would like it to be, but still I hope that practically it is detectable. And the bottom line of this experiment is the following. If we let our sphere and a ball comparably sized in mass and in radius execute small angle oscillations about the pivot point that sits on the periphery of each object, then such a period of small angle oscillations of a sphere of a hollow body will be strictly larger than the corresponding period of a ball. Again, that number, that ratio is not as pronounced. I think it's again 1.09, so maybe it's not as good. Again, if there are people in the audience who are good with experimental physics, they can tell us how this experiment may be improved. And again, maybe this solution of the problem is not as good as the other ones. Once you inhale all 5, see what do you think, which one of these 5 solutions is the better one, or which one is more experimentally favorable. Now that we're done with the solution number 4, we will move on to the 5th and the final solution of the problem, S3P3. For the 5th and the final solution of the problem S3P3, my idea was to do the things that are opposite to what Sisyphus apparently was doing back in the time, rolling a rock up a mountain or up a hill. Here we will roll our spherical chickens of uniform density, hollow to represent a sphere or solid to represent a ball, down the inclined plane as shown by the blue velocity vector over here. This time the rotation of our object will be this way as shown with this orange arrow for the omega, for the angular velocity. Our thing will roll without slipping again. That's the pure definition of rolling. With friction, the force of friction will be applied to the pivot point over here, T, the point of contact, the point of tangency, shown in red, the force of friction. The force due to gravity is shown over here in green. The angles between the force of gravity and the direction, which is defined by the tangency point between the object of revolution and the inclined plane. This is angle theta here, this is angle theta. And the idea here is the following. Compute, this time just for sake of variety, compute the magnitude of the linear acceleration AC of the center of mass of both objects, a sphere or a ball. And then again, hope that it will be possible. This formula will have enough tactical juice in it so that it will be possible to discriminate the linear acceleration of a sphere versus the linear acceleration of the center of mass of a ball. Again, we already understand by the time we solve the problem number 5 that the moment of inertia of the spherical chickens of uniform density should play a central role. And once you understand what is going on, then we recommend that you put this video on pause, walk away, and try to solve this problem on your own, and then come back and compare your results with ours. Again, because I want to keep the size of this episode manageable, I pre-wrote the gist of the solution of this problem on the right side of the board, and you are more than welcome to solve it in any other way because there are many different ways in which this problem can be solved. The way I chose to solve this problem is based on the equations of the torque equation of rotational motion about an instantaneous axis. And this time, this is instantaneous axis, we will take it that it passes through the point of tangency T, where our spherical chicken of uniform density that models either a sphere or a ball comes into contact with the inclined plane down which it's rolling without slipping, but with friction this time. But the beauty of this approach over here is because any vector that passes through the axis um, about which we will be constructing our torque equations generates what? Zero torque, exactly. So the friction generates zero torque, and the force, the normal reactionary force, generates no torque because again it passes through that instantaneous axis. So here the idea is the following. In general, the velocity of the let's say we will call this point C, the center of mass C. The velocity of the center of mass C is comprised of two velocities. The linear velocity of the point T, the point on the periphery of the rolling object with respect to the inclined plane, because for example if the object somehow slides down in addition, then the linear velocity of that point will be non-zero. But in our case, because there is no slipping and our object is rolling down the inclined plane, the linear velocity of that point will be point T will be zero, and there will be only rotational component omega r, where omega again is the angular velocity with which our spherical chicken of uniform density rotates about its natural axis of symmetry. So the torque equation, again, we looked at it already. The first time derivative of torque in this case is the moment of inertia times the first time derivative of the angular velocity. And in this case, there is only one force that actually generating that torque. That is the force due to gravity mg. So in some sense, imagine that we tied a little rope to the center of mass of our object and we're pulling on it. So eventually, of course, it will try to rotate that object precisely about this instantaneous axis that passes through the point T, like so. And that is exactly the r is the distance from the center of mass to the instantaneous axis from the point of application of the force, center of mass, axis T, distance r, and this time the angle between, remember the vector product between the force mg and the radius vector is computed which way? Counterclockwise in the positive direction. So precisely the sine of the angle between them, sine of theta. This is pretty much it. And now once we understand that because there is no slipping, here the velocity of the point T with respect to the inclined plane is zero. There is no slipping. So here the velocity of the linear velocity of the center of mass of our object of revolution, rigid object of revolution, only connects to the angular velocity of that object as it rotates about its natural axis of symmetry is this, and then the rest is straight up basic arithmetic of derivatives. The acceleration is the first time derivative of the velocity, and the velocity will be the first time derivative of the angular velocity because r, evidently, we have to treat this equation as equality as a product of two functions. So here we'll have first derivative of omega times r plus omega times first derivative of r, but r remains the same. the first derivative of r evaporates, so we have only this expression left. And where do we take this guy from? We take it from this equation that is due to the torque equation of rotational motion, and that's it. The game is over. Then we have the expression mgr squared times the sine of the angle theta remains constant, the angle under which the plane inclined with respect to the horizon, divided by the moment of inertia with respect to the axis that passes through the point T right here. And again, by the corresponding parallel axis theorem, we already know how to compute that moment of inertia. It will be the moment of inertia about the natural axis of symmetry of this object plus m times d squared, where d is the distance from the pivot point and the center of mass, which is r. So this is mr squared, and m here, the object, I'm sorry, here, this is the point C, the moment of inertia with respect to the center of mass C. It's better to call it C. Maybe some people want to call it O, it doesn't matter. But here we have this equation right here. Once we put this equation into here, into the denominator, then what will happen? Well, we divide both sides of this result by mr squared, and what will happen? Look at this. Mr squared in the numerator is gone. Mr squared here is gone, so we'll divide the moment of inertia with respect to the axis that passes through the center of mass, IC. And this is what we have. To be consistent, IC. And now what do? Well, we carefully compute the moment of inertia of a sphere about its natural axis of symmetry, already known to us, 2/3 mr squared. We put this result into this formula, and mr squared in the denominator and mr squared in the numerator cancel out. We have 1/1 plus 2/3. Multiply everything by 3. 3 goes in the numerator, 5 goes in the denominator. So the linear acceleration of the center of mass of a sphere when it rolls down in the prescribed fashion down the inclined plane will be 3/5 times g, the acceleration due to gravity, times the value of the trigonometric function of sine of what angle? Of the angle of the incline. And the moment of inertia of a ball with respect to its natural axis of symmetry is 2/5 mr squared. Same exact maneuvering, but this time 1 plus 2/5. 5 goes into the numerator, 5 plus 2, 7, 7 goes in the denominator. So the linear acceleration of the center of mass of a ball as it rolls down the inclined plane will be 5/7 times g, acceleration due to gravity, times the value of the trigonometric function of sine evaluated at the angle theta, which is the angle which our inclined plane makes with the horizon. Game over. We can either compare 3/5 to 5/7, or we can, as usually we do it, we can construct the ratio to erase the material that does not really affect our experiment in any substantial way. So the ratio of these two accelerations will be what? 3/5 times 5 in the denominator, 7 in the numerator, 21/5, less than 1. This is a real number that is strictly less than 1. And that means what? That means that the linear acceleration of the center of mass of a sphere will be strictly less than the linear acceleration of the center of mass of a ball as both objects roll down the inclined plane. And that means that the rate with which the velocity of a sphere grows will be smaller or lower than the rate at which the velocity of the center of mass of a ball grows. So in some sense, we can say that our fearless prediction that when both objects, for example, rolled from the same height under the same conditions with zero initial everything, angular velocity, linear velocity, then the ball will reach the bottom of the inclined plane ahead of a sphere. Again, the intuitive explanation is because all the mass of a sphere, all the mass of a sphere is located as far away from the center of that geometric center of that object as possible, and the effort that needed to be applied to that object to get it rolling must go, intuitively speaking, through the entire length of the radius of that object. Conversely, when we have a ball, it is not the case that all the mass is as far away from the center. It's actually the other way around. We have quite a bit of mass immediately around the center, some more mass around it, and around and around. So, in plain English, intuitively, it's easier to get the ball rolling, so to speak. That's the popular saying in English. So it is easier to get the ball rolling than a comparable sphere. So in a sense, it will accelerate faster and get to the bottom of the inclined plane ahead of a sphere. And that is how these two objects can be discriminated one against the other with absolute certainty and correctly. Now, this is it for the physics problem S3P3, and we will move on to a new challenge next. Our next challenge will be a problem in computer science. The next computer science problem, season 3, CS3, if I'm not mistaken. And the objective of this problem is the following: come up with the single pass. This is the key in this challenge. Single pass algorithm that will take on its input a finitely, evidently sized array which contains ones and zeros only and no other elements. Or these zeros and ones are just logical, if you will, representations of two mutually exclusive types of objects. Could be squares and circles, for example, for all we care. So as an abstract theoretical notion, our array contains only ones and zeros and nothing else, and all the entries are taken and occupied either by 0 or by 1. So the objective here is to invent a single pass algorithm that will take such an array on the input and on the output in place with the space complexity of big O of 1, sort this array in such a way that, for example, let's say arbitrarily, on the left of this array there will be all zeros. First, all zeros will go, and on the right side, on the right extremity of this array, there will go ones. 1, 1, 1. In other words, sort the two mutually exclusive, two distinct types of objects in such a way that all the objects of one type contiguously gravitate toward one extremity of the array, and all the objects of the other of the opposite side gravitate towards the opposite extremity of the container of the array. Let's say the size of array is given, it doesn't really matter. And here, again, all these clever C maneuvers of mem said this, mem said that do not work. This is not, we will not accept it. The idea here is to come up with a beautiful, beautiful computer science idea for a genuine sorting. How would you come up with a way to sort these objects in a genuine way where things happen in a non-trivial way? This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the computer science problem S3CS3.